The color of Mars is not actually red. Mars, the red planet, definitely looks red when we observe it. Since ancient times, it has been observed by humans, and Egyptians called it the red one. But the color of Mars is not actually red. Sure, it looks red to us, and the surface too looks red because of various forms of ferric oxide present in Martian dust. But if you get a close-up view of Mars with an orbiter or rover, the red color doesn't last that long. Once you go only a few millimeters deep, it isn't red. What might be the reason behind that? Let's talk about the reason behind that in this video. Earth is a beautiful planet, that we can all agree on. When we look at Earth from space, we see a number of diverse colors. The color of our sky is blue, and sometimes this blue color is because of the atmosphere that scatters shorter wavelength blue light preferentially in all directions, giving it its distinctive color. However, during sunset, light must travel longer through the atmosphere. As the sunlight travels further, the shorter wavelength blue light is scattered further, and we perceive the longer wavelength yellow and red light. The oceans are also blue because the water molecules absorb longer wavelength red light better than blue light. Meanwhile, the continents seem brown or green depending on the lack of abundance of flora that grows there, and the ice caps and clouds are constantly white. But on Mars, the dominant color is red. The ground is red, the highlands are red, the lowlands are red. The atmosphere, even though it is very thin, looks red. The lowlands are red, the mountains and sand dunes are red. The color red is everywhere. The only exception are the clouds and ice caps, which are white with a slight reddish tint as they are observed from Earth. Yet, quite surprisingly, the redness of the red planet is very shallow. Even if we dig just a few millimeters beneath the surface, the redness vanishes. In order to understand why that is the case, we first need to understand why Mars looks red in the first place. Its redness has been the most prominent feature of the planet across all languages, cultures, and history. The Sanskrit word for Mars is Mangla, which means red. Its Egyptian name, Har-Dishir, literally means the red one. As humanity has progressed over the years in space technology, we have taken photos that clearly show that the air above Mars has an intrinsically red color. Rayleigh scattering prevails in the Earth's atmosphere, flinging blue light in all directions, while red light goes largely unaffected. However, because Mars's atmosphere is just 0.7% as thick as Earth's, Rayleigh's scattering from gas molecules in its atmosphere has a minor effect. Instead, dust particles in the Martian atmosphere dominate in probably two ways. The first reason might be the greater absorption at the short optical wavelengths of about 400 to 600 nanometers. And the second one is because of the larger dust particles, 3 microns or larger, that scatter longer wavelength light more efficiently than atmospheric gas particles that scatter shorter wavelength light from Rayleigh scattering. If you observe the suspended dust particles on Mars, you can learn a lot about how it affects light. This dust is very similar to the regions on Mars that have high reflectivity and are rich in iron. Using ESA's Mars Express mission Omega tool, scientists were able to know that the most frequent type of dust on Mars comes from nanocrystalline red hematite. It is made up of particles very tiny in size, between 3 to 40 microns, which gives it the ideal size and composition for the Martian winds. The swift Martian winds continually sweep vast volumes of dust up into the sky, where it remains quite well mixed even when no dust storms occur. Once you start observing the Martian surface carefully, the story gets more interesting. Ever since observation of Mars started in detail, first from orbiting spacecraft and later by landers and rovers, it was observed that the surface features would change over time. There are darker and brighter areas on Mars, and the darker areas would evolve in a never-before-seen particular pattern. They would seem dark at first, then they would be covered in dust from brighter areas, and then they would go back to being dark once again. We didn't know why for a long time, until we saw that the dark areas that changed all had a few features in common, especially when contrasted to the dark sections that didn't change. The dark regions that changed over time, for instance, had lower altitudes and smaller slopes that were bordered by lighter areas. The higher elevation, steeper slope, and extremely extensive black patches, on the other hand, did not alter throughout time. Carl Sagan found the reason for this. Mars is blanketed in a coating of this fine sandy dust, which is carried by winds across the Martian surface. This sand is blown from place to place, but it prefers to move small distances from higher to lower elevations, or to equivalent heights, rather than up to much higher elevations, and be blown off of steeper slopes rather than shallower slopes. In other words, the red dust that dominates Mars's color palette is only visible on the surface. In this case, that's not even a lyrical flip of phrase. Most of the planet is coated by a layer of dust barely a few millimeters thick. Even in the deepest part, the Tharsis region, which consists of 3 extremely massive volcanoes barely offset from Olympus Mons, which appears to be the plateau's northwest, the dust is believed to be just 2 meters or 7 feet thick. You might look at this and wonder whether the topographic map and the ferric oxide map of Mars coincide or not. But before we come to that question, you need to understand that ferric oxide doesn't necessarily mean red Mars dust. Ferric oxide is present everywhere on the planet, in the crust, in the lava flows, and in the Martian dust. As a consequence, when we look at a ferric oxide map of Mars, created once again by the fantastic Omega instrument on board ESA's Mars Express, we see that while ferric oxides are found everywhere, their abundances are highest in the northern and mid-latitudes and lowest in the southern latitudes. The topography of Mars reveals that the elevation varies in an unusual way throughout its surface, and that this variation is only partially connected with the presence of ferric oxides. The highest heights are found in the ferric oxide-rich Tharsis area, although the concentration of ferric oxides decreases in the lowlands to the east. Also, the red hematite isn't the only possible form of ferric oxide present on Mars. There is also magnetite, which is black in color. What we believe is happening, and this has been a constant image for many years, is that there is a brilliant, globally dispersed, globally homogeneous collection of dust that is swept up into and remains in the atmosphere. That dust is essentially hanging in the thin Martian atmosphere, and while occurrences like dust storms might increase the concentration, it never falls to a negligibly low level. Mars's atmosphere is usually rich in this dust, which gives the atmosphere its hue, yet the color aspects of Mars's surface are not consistent at all. The settling of atmospheric dust is simply one component in defining the hue of its surface. Mars isn't a uniform red tint, as we've learned from our landers and rovers. In truth, the surface is more of an orangey butterscotch hue overall, with numerous rocky objects and deposits on the surface seeming to be a variety of colors: brown, golden, tan, and even greenish or yellow, depending on the minerals that make up those deposits. One question that we still need to answer is how red hematite particles are formed. Hematite may be obtained by a purely physical process, erosion. When magnetite powder, quartz sand, and quartz dust are mixed together and tumbled in a flask, part of the magnetite changes to hematite. A black combination, dominated by magnetite, will turn red when the quartz fractures, exposing oxygen atoms that bind to the broken magnetite bonds and produce hematite. Perhaps the assumption that water is responsible for ferric oxides is, after all, a literal red herring. So in all, the color of Mars is red because of hematite. Even though ferric oxides are found in many places, only hematite is largely responsible for the red color, and the small dust particles suspended in the atmosphere of Mars coat up the top few millimeters of its surface. If we could somehow quiet the atmosphere over lengthy periods of time and let the Martian dust settle, you think Rayleigh scattering would prevail, rendering the skies blue like it does on Earth. However, since the Martian atmosphere is so thin and tenuous, the sky would seem exceedingly dark, almost entirely black, with a little bluish hue. Even during the day, if you could effectively block out the brightness emitted by the planet's surface, you would be able to see certain stars and up to 6 planets: Mercury, Venus, Earth, Jupiter, Saturn, and maybe Uranus. Mars is known as the red planet, yet just a tiny fraction of it is red. We observe the outermost layer of Mars, and to us it looks red. So what do you think about its color? Can you think of other planets which might deceive us like this? Let us know what you think in the comment section below, and share the video with your friends.